Bismillahirrahmanirrahim. In last lecture, lecture 5, functions, we have talked about what are the functions and then their types and discussed some in examples. I will again start with an example today. So the example we will use to talk about the function, its type onto, and then one. So let's say we have a function. Consider the relation f from z into z. So this is the relation, so still we cannot write that, so you just write from z into z defined by for all n in z f of n is 2n is the previous example which we have here, that f was from z into z defined by f of n. F of n is n squared for all n z. We now have f of n is 2n. We show that f is a function. So, and then to do that, to show f is a function, take n comma n prime from z, n comma n prime in z, and suppose that f of n is f of n prime, then 2n is 2n prime, i.e. n is n prime. Hence, f is a 1 function, because two different elements of z does not have the same image. And if they have the same image, then the elements are equal. Now, since for all n in z, f of n is an even integer, and we see that an odd integer has no pre-image, has no pre-image. Thus, f is not onto Z. However, f is onto E, the set of even integers. Perfect. Now, this is how we use some definitions and show that which function is onto and one. Now let's combine the functions and talk about a different function. So we have a definition. One 1.5.10 says that let A, comma B and C be non-empty sets, and if A to B and G B to B into C are the functions, the composition of F and G written GOF is the relation from A into C defined is follows. Defined as follows that G of F is nothing but x comma z, given that x in A comma z in C, and there exist y in B such that f of x is y and g of y is z. G of f is such relation. This is how we combine the functions. So this is a composition of relations, and then we can say let if A into B and G B into C and x comma z is in the composition of G of F, i.e. if we apply this G of F on this x, we will get G of F of x, which is z, or we can further write G of y, which is z for y in B. Perfect. We will have a theorem now, which in which we talk about these functions. So theorem 1.5.11 says that suppose that if A into B and G B into C are two functions, then number one, G of F is a function from A into C, i.e. function from A into C. A into C. Two, if F and G are 1, 1, then G of F is 1, 1, 3. If F is onto B and G is onto C, then G of F is onto C. We can prove these, but they are very simple. So not actually needed to do that. Example, consider the function if z into z and g z into e, where f of n is n square and g of n is 2n. 2n for all n in z. Then g of f is z into e and g of f of n is g of f of n, which is g of n square, which is 2n square, 2n square. This is how we can compose functions. Theorem. Thirteen. Let if a into b be a function, g b into c be another function, and h c into d be another function. Then we can combine these three functions compose these three functions as follows. And this composition operation is associative. So that is composition of functions is associative. And we can prove this. So first, note that I can also prove the previous theorem, but it is long, so it will take time. So this is the short one. That's why I'm giving the proof. First, note that H compose G of F is a function from A to D, A into D. And H compose G compose F is a function from A into D also. Now let X is in A. Then we have H compose G compose F of X, which is going to be H of G of X, and then it will be H of G of F of X. And this can be written as H compose G of F of X. And this can be written as H compose G compose F of X. And so it is proved. Point to note. So let's say we have two sets, let A and B be sets. A and B are said to be equivalent written as A equivalent B if there exists a 1-1 function from A onto B, i.e. the elements of A and B are in 1-1 correspondence. And by 1.5.11, it follows that this is an equivalent relation. If A and B are equivalent, then sometimes we write mod of A and B the same. So let's talk about the lemma. Now we have a lemma. Lemma 1.14 says that let A be a set and F A into A be a 1 function then power n A into A is a 1 function for all integers n greater than or equal to 1. For the clarity, if 1 of x is f of x, if n of x is f compose f n minus 1 of x for all n in n. Now we know this, and then we will prove this lemma. So suppose there exists n greater than 1 such that power n is not 1, let m is greater than 1 be the smallest positive integer such that f power m is not 1, then there exists x comma y in A such that x is not y and power m of x is f power m of y. But then f of f power m minus 1 of x is f of m minus 1 of y. And hence f of m minus 1 of x is f of m minus 1 of y since f is 1, Now, since m is the smallest positive integer such that f is not 1, 1, integer such that f power m is not 1, 1, f power m minus 1 is 1, 1, 1, 1. Hence, x is y, which is a contradiction. Which is a contradiction. Thus, f power n is a 1, 1 for all n greater than or equal to 1. This is the proof. So what we did, we just supposed that there is n greater than 1 for which f power n is not 1, 1. And then we suppose that there is m greater than 1 be the smallest positive integer such that f of m is not 1, 1. And then we carried on. And then we suppose that we show that f power m minus 1 is 1, 1. So x and y are equal because we have assumed that they are not equal. So eventually they become equal, and then this become 1, 1, then they become equal. That's why f power n is going to be 1, 1. We have another theorem says that theorem 1.5.15 let A be a finite set if A into A, f such that A into A is 1, 1, then f is onto A. The condition is A should be finite set. Then if f is 1, 1, then A will be onto A. And prove this. Take let y is in A. Now, if power n pi is in A for all n greater than or equal to 1, hence we will set y, f of y, f square y, such that so on is a subset of A. Now, since A is finite, all elements of the set S cannot be distinct. Thus, there exist positive integers S and T such that S is greater than T and f of s, f power s of y is f power t of y. Thus, power t of f power s minus t of y is power t of y, hence f power s minus t of y is y, since by lemma 5.14 f power t is a 1 let x is f power s minus t of y and a, then f of x is y, hence f is a. F is 1 to a. Perfect. So provide a definition that says very important concept about functions. Let a and b be sets, and f is a function from a into b. Number one, f is called left invertible if there exists g from b into a such that g of f is identity function of a. 2, f is called right invertible if there exists h from b into a such that if compose h is IB, identity function from B. In general, a function f a into b is called invertible if f is both left and right invertible. Usually we talk about the invertible functions, but as you go into the deep, you can talk about left invertible and right invertible functions. Perfect. Let's talk about an example. Let f is a function z into z, and g is a function from z into z. Both are defined below as follows. That f of n is 3n, g of n is n over 3 if n is multiple of 3. Otherwise, it is 0 if n is not a multiple of 3. And this is true for all n in Z. Now, we compose them. F of g of n is going to be f of g of n, which is going to be f of n over 3, n over 3, which is where this is going to be 3n over 3, which is going to be n and 0. If n is multiple of 3, if n is not multiple of 3. Hence, f of g is not Iz, but g of f of n is g of f of n is g of f of n, that is g of 3n, that is n for all n in Z. Thus, g of f is Iz. Iz. Hence, g is left invertible of f. Now, to determine which function have left, right invertible or both invertible, we have the following theorem. One point 5.18 says that let A and B be two sets, B sets, and if A into B is a function, then following assertions hold. 1. F is onto, sorry, F is 1, 1 if and only if, that is 1 double F, is left invertible. 2. F is onto B if and only if F is right invertible. 3. F is 1, 1 onto B if and only if F is invertible. Another story for the functions which are invertible or not. Definition. We provide the proof for this theorem on demand. If someone asks me in the comments, I will provide that. Number 1.5.19, let f a into b be a function and a prime be a non-empty subset of A. The restriction of F to A prime written as F restricted to A prime is defined to be F restricted to A prime is a function, the set X prime F of X prime, given that X prime is an A prime. We say that F restricted to A prime is really a function F, except that we are considering the function F on a smaller domain. Okay. Then another definition, 1.5.20 says that let F is a function from A prime to B and A be a set containing A prime. Function G from A to B is called an extension of F to A if G restricted to A is F. G restricted to A is F. I will give an example. We have a function from even integers to z, and we have another function from z to z, where f of 2n is 2n plus 1, and g of n is n plus 1 for all n in z. Then g is an extension of f to z, and f is a restriction of g to e. Let h be a function from z into z given by, for all m in z, h of m is m plus 1. If m is in E and h of m is m, if m is in E and h of m is m, if m is in not E. If h of m is m plus 1 if m is in E, and h of m is m if m is not in E. Then h is an extension of f to z. However, h is not g. Thus, a function may have more than one extension. More than one extension. And then I've done the last part of this section. We will provide the worked out examples. Thank you so much for watching.